Okay, so the good thing from your perspective is that section 7, you're not actually learning anything new. So it's not like we're learning another thing like quotient rule or product rule. Section 7 is just going through and trying to look at a lot of different parts of derivatives and trying to figure out what they stand for. So nothing new, just a lot of various little things that if we don't stop and go over are kind of really easy to just lose sight of and get lost on details. So we've just got a whole bunch of pages of little things, but nothing new. I'm going to skip over some of it for sure. But like if there's something you desperately want to know, I can certainly go over it. But so you do have the answer keys to this, and so if there's something I missed, you can certainly look it up there too. But I want to try to focus on what I think would be more important to you. I don't know. We'll go through it. It's kind of an awkward section for me to try to go over with you because there's nothing. I'm not teaching anything. Like this is just us kind of going through things together. So that's good and bad, I'm sure, but we'll do it. Okay, let's look at example 1. It says, suppose that S equals f of t gives the distance in feet of an object from a fixed point as a function of time t in seconds. So it's basically just telling you what S is. Okay? What's the common term for ds dt?
T.
I think I know what we need to do. You guys look like you are doing your best to avoid saying anything today. My first hour told me we should shake it to see if we can throw it off to keep the same people from getting called on. Because it feels like some of these are weighted or something. I don't know. How did I do that?
I tried my best.
Yeah, I don't have good eyes. 9. I actually rolled 2 people somehow. I didn't even turn it. Who's number 9? Magdalene. Thoughts on ds dt?
Speed over time, so acceleration.
Okay, where are you getting the speed from?
V of S.
Oh, just the S portion?
Yeah.
Got it. That's actually pretty good logic, but it's not. So up on the top, it says that S is in feet. So S is distance in feet.
Distance over time is v velocity.
Perfect. You're right. Otherwise, S logically seems like a speed or something. So this is going to be distance per time. So feet per second. I mean, you basically can read it as it says. So ds dt is the rate of change of the distance compared to the time. It's like saying delta S over delta T. So it's slope. Okay. Describe the following notation in real world terms. ds dt line t equals 4. Who was that next number? 20, I think it was? It was not 20, it was 24. Andrew. Okay, so we just talked about ds dt is talking about the velocity or feet per second. You know what? I did not even write velocity up there. I don't even know if we said the word now that I...
So is it like, what is the velocity when it's 4 seconds?
Perfect. This is asking you to find the velocity when the time is 4. So this is, what is the velocity or feet per second there's lots of ways you could say this. There's no like exact. phrase has to be. As long as you recognize this stands for velocity at that time. That's the key part there. Okay, so reading notation. Oh, then we get to C. What is the real world meaning of f prime of 4 equals 18? Should we do this one together, or do you feel like we could call on somebody for this one? Should I just, does anybody think they know this one, rather than me just, like rolling? Luke?
I have a guess.
Okay, that's perfect.
Acceleration.
Yes, we don't technically know it's acceleration, but yes. So what it's going to stand for is how fast is the velocity changing. So it's the rate of change of velocity. So it's how fast the velocity is changing. Now we actually have numbers. We actually have numbers to work with here. What you're saying is acceleration is correct and good. And I 100% would take that answer. So if we're trying to say how fast the velocity is changing, the 4 inside the parentheses means that it's at time 4. And an answer of 18 means the velocity is going up 18 feet per second per second. Because 18 feet per second represents the velocity, and the little prime means how fast that is changing. So it'd be 18 feet per second, which we usually say feet per second squared or acceleration. Yeah.
Isn't f prime of t, in this case is 4, the same thing as ds over dt? So wouldn't we still be talking about the same thing?
Oh my god. Yes. You waited till I got all the way to the end.
Sorry.
Yes. I'm going to blame Luke. Yeah, I got all the way to the end of that without even really looking. F is the same thing as S. S prime is the same thing as ds dt. So what I could do to fix this mistake is it's how fast the distance is changing at t equals 4. So instead of saying velocity, I'll say the distance is increasing at 18 feet per second. And then it's fixed as if it never happened. Nice catch. Otherwise, that would have really ruined our notes. That does explain why we weren't doing acceleration yet. We're pretending acceleration doesn't exist until we talk about it. Okay, now this kind of leads us to number 2, which is actually more of like an actual problem with the setting, which usually is easier to visualize. Now, what I don't like is this starts off by saying, did Neil Armstrong step off the lunar module? I feel like this lady is one of the moon conspiratorists. Like, she's trying to get you going right away.
Moon landing was fake.
Right. So we'll put Max up here with this one. Okay, so did Neil Armstrong step off the lunar module, pick up a rock from the surface of the moon? If he did, I like still questioning it. If he did, scientists say that the rock would have a velocity of 24 meters per second. The height of the moon rock can be modeled by the function s of t equals 24t minus 0.8 t squared meters in t seconds. Find the velocity and acceleration of the moon rock as a function of time. Now, we touched on this really briefly the other day when we had position, velocity, acceleration. So velocity is going to be the derivative of position, which is kind of what example 1 was. Okay, so if we have s of t equals 24t minus 0.8t squared, v of t is going to be the derivative, which is 24 minus 2 times 0.8, which is 1.6, t to the first. And then acceleration would be the derivative of velocity. And that's because acceleration means how fast is your velocity changing. Okay, so acceleration equals negative 1.6. And that's the gravity constant for the moon. Okay, B, this is where students do start to get stuck. I'm going to guess those who've taken physics are pretty used to these questions, just because I believe you had them at the beginning of the year. Yeah. And if you haven't had physics, I'm going to treat this as if none of you have had physics, because those who haven't probably have never done these questions. So it says, how long will it take for the rock to reach a maximum height? Now, it's a very valid question. What's annoying for most students is that it doesn't tell you what to do. It doesn't tell you to find when the velocity is 0. Because if you're talking about a rock going up, pausing, coming down, we're trying to find when the velocity is 0. So we're going to take the velocity function and make it equal to 0. Um, 15? So it took 15 seconds for the rock to reach maximum height. Now, are you guys okay as to why we're trying to find when the velocity was 0? Like, I'm assuming in your head you can kind of picture throwing something up and then it pauses at the very top. So the split second that it pauses is when its velocity is 0. Now, velocity does have a direction if you're not really familiar with velocity. So if your object is traveling upwards, your velocity is positive. So you're going to have the fastest velocity right at the beginning, and then it slows down because the rock or whatever is being pulled by gravity. And then at the split second when it stops, the velocity is 0. And then it starts coming down, so velocity is negative, and then the velocity is getting larger because of acceleration. And that's kind of how you have to visualize a lot of these story problems, which, for better or for worse, is what happens. But most people can kind of picture it in their head. Okay, then we get to C. How high did the rock go? When did it hit the ground? Is this something we should probably talk through together as well?
Yes.
Okay, I can do that. So B says, how long does it take for the rock to reach a maximum height? So we know the time when the rock was at the highest spot. C says, how high was that? What we're going to do is we're going to take the time answer that we just figured out and plug it in the position function. Because the position function tells you the height of the object at any time. So I'm going to take the position function and plug in 15 seconds. So S of 15. Oh, I should really have a calculator on me. Oh, wait, I have an answer key next to me and I totally forgot about that. Let's pretend I know how to do this in my head. 180. Look at that. Human calculator. The label I'm going to put after it is meters. That's why I went to look at the problem. Because each problem will be kind of set up slightly different. I know in physics they exclusively use meters for the most part. in calc, it switches on and off between meters and feet, so, you know, just pay attention to it. Okay, so that was the actual height. Now the second part of the question says, when did it hit the ground? This one I feel like I can call on somebody. 30, 20. Come on. Would you like me to guide you slow? Okay. What's the height of the object when it hits the ground? No, that's the height of the object at the top. What's the height of the object as it hits the ground? 0. Yeah, so at the very top it's at 180 meters, and then since the question is phrased when it hits the ground, that's a height of 0. So I don't know a time, and the reason I'm emphasizing that, time is the number that you can plug in, but we don't know the time. What we do know is the answer is 0. So I'm going to take the height position, the height function, position function, and I'm going to set that equal to 0. Because when I'm done, that'll tell me the time that would give you a height of 0. Let's factor out a 0.8 t or just a t. So one answer is 0, one answer is going to be 24 minus 0.8 t, 30. Oh yeah, it's going to be 30 seconds because it took 15 seconds to get to the top. Now, you can solve this quadratic equation however you want, whether it's factoring, whether it's quadratic formula, whatever. I don't really care about that part. We're not focused on that. But I got 2 answers. It doesn't really hit the ground at time 0 because that's where the rock was, and apparently he picked it up and just threw it in the air. I'll be honest, I haven't actually watched a video of the moon landing, so I don't really. Like, I think it's cool, but I don't think it's cool enough to like sit there and watch it.
It's not real.
Well, okay, then there's that too, right. Somehow that's become popular now. That is almost like flat earthy. Not?
I'm not a flat earther.
Oh, I see, but there's no such thing as the moon either then. Okay.
Well, there is a moon, but there was no moon landing.
Why did they land on them?
It was like in a NASA lab. They put in a bunch of green screens. I saw a YouTube video.
I like how you're using your cell phone that uses the satellites that are in space already. Mm-hmm.
Well, it's not on the moon.
Which is in space.
Well, allegedly.
So allegedly we can't get to space, but you're using technology that uses space.
No, I think he's saying that they landed on the moon later, but at the time where Neil Armstrong stepped on the moon, it was staged.
Yeah,
It was
the
fake.
footprint on the moon didn't match.
I feel like you've done way too much research on the fake landing theory.
No, I just know about it.
Oh, that does not sound like you just know about it.
No, I've not watched the same.
You've listened to Max way too much.
Yeah. Starts to happen when they got back.
Okay, are we okay with example 2?
Yes.
All right. I told you I was trying to go kind of slow today because of the other hours.
What time do we get out?
That's a good question. 44. Okay. So this says rates of change other than motion. So motion is just the most common that we run into, but it can be applied to anything. Derivatives represent how fast something changes. And you guys are going to get lots of story problems throughout the year / on the AP test that represent really weird situations. A couple years ago, the story problem was about how fast bananas get taken off of grocery store shelves and how fast they get restocked. Yep. The year before that was about putting a baked potato in an oven and how fast it cools off, and what was the one before that? So there was the banana one, there was the potato one.
It must like food.
There was a pizza one.
Oh, yeah. They're
Um,
hungry when they wrote these.
well, yeah, it's a 4-hour test, so they're just trying to be cruel. So,
Oh,
you get really hungry in the middle of it.
4 hours.
Shoot, I can't remember it. Everybody made fun of it a lot because it was just a weird situation. The banana one was by far the strangest, but at least it was realistic. Like you can picture it. Okay, so
You know, there's like
here, this one says W stands for the daily quantity of water in gallons required by a palm tree of height X feet. And I don't know if this is true or not, but I found it kind of interesting. If you guys watched Dune yet, this is part of Dune. Explain the meaning of each expression in a complete sentence, including units. W25 equals 38. $11? Abby's gone. I was just going to say, I'm surprised we haven't rolled somebody that's not here. 10? Hunter? You're 10. What does W25 equals 38 mean?
In 25 days, you have 38 gallons of water.
It's actually not a bad thought. I mean, like, that's pretty good reasoning. So 25 to you was the number that was being plugged in. 38 meaning the gallons of water required. So the 38 was perfect. But in the problem, it just very briefly tells you what X stands for. So it's not number of days. It stands for a 25-foot tree. So the number being plugged in represents the height of the tree. Okay, so this is basically saying a 25-foot, what was it, palm tree? 25-foot palm tree requires 38 gallons, which is an awful lot.
Is that actually what it said in the movie?
In the movie Dune, on that planet that's all desert dust, they have palm trees. They've been growing for a long time, and somebody's job is to water it.
Wasn't Zendaya in the movie?
Not true.
Hmm?
Yeah, she is.
I think it was per day in the movie. Yeah.
And then Timothy too, right?
No idea who that guy is.
Chalamet?
I know.
He kind of looks like
But like this kind of makes sense to me. But I'm kind of curious. Like I'm assuming that palm trees suck up water in humid areas. So I'm wondering if that 38 gallons. How do they measure that? But still. So I don't know if this is real, but I thought that's kind of cool.
No keeping in gallons required by a palm tree of the height of X feet.
Yes.
At the very end, that's underlined is where the height of what X is, and 38 gallons of water in space. Call it.
So we're kind of hearing what you're talking about. What was the question though?
Oh no, he just asking me like how.
I was wondering why W of X, because if W of X is a gallon of water, so I was wondering why 25 is a gallon of water. Because would that be W of X?
Oh, so W of X means the answer of WX is how many gallons required.
Gotcha,
And then at the end, when it says a palm tree of height X feet,
gotcha.
then it's trying to say that X is the input, the answer is the gallons. Yep. No, that's needed for part B, so that's good you brought that up. I don't know if I should call on anybody for this one, but do you guys, this is inverse,
Oh, yeah.
right? Okay, so inverse. That means whatever is in the parentheses represents the exact opposite. So these two numbers are inverted. That's what an inverse function is. So the inverse of W would mean if you know the number of gallons required per day, you would be able to tell the answer as height of the tree. So this one is saying a 38 gallon per day tree. Boy, that sounds really weird to say. 38 gallon per day. I better write it, otherwise I'll. a 38 gallon per day tree is 25 feet tall. So you're going to start running into inverses this year, and you kind of have to understand how they're laid out. And if you kind of knew this one already on your own, very nicely done. Okay, C, and then we can probably stop after there. Yes. The air conditioning one I thought was a bad problem. I don't want to do the air conditioning one. It almost like made it more confusing than it was worth. $29. Rosa, you get called on a lot too, I think.
Yeah, number or letter C.
Yes.
So, so would that be like in 25 days? Because it's like the
So in the derivative, the variable is still going to represent the exact same thing. So if the original W of X would stand for the same item. So,
it's 6 days.
uh,
No.
okay, that's all right. So 25 is going to represent a 25-foot tree. Okay? Does anybody want to take a guess at this?
So I think it's saying that a 25-foot tree requires 6 more gallons of water than like a 24-foot tree.
Good. That's very good. So this is the rate of change of daily water required. So this is how fast the daily water required is changing. And I'm phrasing it that way so that it really gets confusing if you say per day per day. So the daily water required six gallons per day shoot, per foot. So it's gallons per day per foot. Because you want to change it by the variable you're using. And our variable on this one is feet, like the how many foot tree. So whenever you take the derivative, it's going to be divided by the variable information. This one is purposely set up to sound weird.
It's like increasing 6 gallons per foot, or 6 daily gallons per foot.
Correct.
Oh, okay.
So like a 24-foot tree, I shouldn't say 6 less. I don't even know how to phrase this one nicely. But yeah, this question was set up this way strangely so that if you can write the derivative, you absolutely know what it stands for. Probably more work than it's worth to comprehend it though.